Welcome back to Introduction to Computer Networks at NTU. This is Polly again, and guys, this is week 12 and episode 21 already. All right. If you go back up, why this is episode 21 is because last week Polly is on conference travel. Recall that you are asked to review 3 videos. Okay. So these are from last semester. So episode 19 serves as episode 19 for the semester. Oh, hi. Hi, Jeremy. Isa, Sylvain. Yeah. Yeah, after a week of offline lecture. Yeah, so this feels a little bit new. All right. Hi. Welcome back. Polly is back. Yeah, so we watched these videos from last semester for last week. Okay. Sorry that Polly was too occupied during the conference week. There's no way Polly lecture, even though I can do it remotely, but it's just not possible. Okay, I'll be exhausted. Okay, hi all. And yeah, so last semester's episode 19 will serve as this semester's episode 19. And last semester's episode 20 and the first hour of episode 21 will serve as episode 20 this semester. So that adds 3 hours of lecture. And what's nice about those recordings is that Polly also, the class from last semester, right? We're working on the quizzes so you guys can follow. Okay. It was a good lecture, good conference. It was very interesting. There are some very interesting papers that people published that Polly is very interested. Okay, and we also published something there. Okay, and you know what? And that takes us to episode 21 today. Okay, 1920, and this is 21. And we have 2 quizzes due this Saturday. Okay. Very few, and there's a good reason for that, because we don't have lectures tomorrow, and it's exam 2 tomorrow. Okay, so if you are not aware of this, ouch. Okay, try the best you can. And by the way, exam 2 is gonna be, as Polly mentioned, a little bit longer and a little bit more challenging. Okay, just do your best. Okay, and allow Polly to remind you. PA8 and PA9, these quizzes are not exactly trivial. It might take more time than you think, so you want to start these early because they are due also, back to back, in fact, the next 2 Saturdays. All right, so that should give you a rough sense what's coming up. And today, we will talk about 2 topics, NAT and IPv6. So these 2 topics are related to an issue we call the IP address shortage problem. Okay, if you recall from the videos last week that you watched, in IPv4, how many bits do we use to represent an IP address? Can you recall? Those who can recall, type up how many bits we use to represent an IP address on the chat. Okay, let's see. I can feel that the delay seems a little bit long this semester. There we go. Hey, August. 24, close, Jeremy. Yeah, I think Jeremy was typing while August is typing at the same time, I guess. Jeremy, very close. I think 24 is more the network part of the IP address, if you recall, right? So if you recall, IPv4, we use 32 bits. 100 points, yes. Very good. Yeah, exactly. That's what I thought. Because in the examples you see very often in an IP address, there's a network part, and there's also a host part. The network part tells which network you belong to, this device belong to. But then there will be a host part to identify the device uniquely. But the whole thing together, okay, represent a machine, right? So together, still 32, okay? Yeah, very close. But hey, 32 bits, that means we can only accommodate 2 to the power of 32 devices. Would that be enough these days, right? I have a smartphone, I have a smartwatch, I have a laptop, I have a desktop in my office. Just Poly, I have 4 devices connected to the internet already. How many devices you have connected to the internet all the time? So obviously 2 to the power of 32 is not enough. That is called the IP address shortage problem. We do have 2 solutions, okay? One is NAT, the other, more formally, IPv6, the next version of IP. In that you will see the IP address space is no longer just 32, it's going to be 128, 4 times longer in the space. But if you count the number of IP addresses we can have, that's a lot more. Okay, so that's the topic today. Now let's start from NAT. It's called Network Address Translation. In this overview video, you will see why we need to translate IP addresses and roughly how we do that, and the surprising benefit of using NAT. So this video, about 5 minutes. NAT, the Network Address Translation Service. This is one of the most used protocols on the internet these days. It's here to address a very serious problem. We're running out of IP address space. Yeah, 2 to the power of 32, it sounds like a high number, but we do have a lot more hosts, a lot more router with network interfaces requiring these IP addresses. Therefore, IP addresses is a scarce resource on the internet. To get one, you pay quite a bit of money. This is also why, okay, if this is home network here behind the local network, your deal with the ISP is often this: you pay a specific amount of money monthly, you get a certain downlink bandwidth, certain uplink bandwidth, and a certain number of IP addresses. Usually you get 1 static IP address or 4 dynamic ones. Okay, if you pay more, maybe 8 dynamic ones. But essentially, the more IP addresses you need being allocated from the ISP, the more money you pay. So it's not like every family can afford paying that much. So to try to save money, this is what we often do at home. Okay, we just subscribe for 1 IP address, and then we create a home network. Okay, using some fake IP addresses that we make up, and subnet address that we make up. So instead of asking the ISP, asking the system admin for a block of IP addresses, we can afford it. We use fake block of IP addresses. So we call this local network or home network. Each of the interface is assigned an IP address on the fake subnet. Okay, so these are then fake IP addresses. Now, as long as we are sending data within ourselves, should be fine. But if we want to send data out, wow, we need to be careful. And that's when we need a NAT server here at the home gateway. So NAT is sitting right here. So all packets that's leaving the local network needs to be using the real IP address, the IP address assigned by the ISP. Otherwise, it's going to be dropped at the ISP. So now if this guy has a connection to go out, and this guy has a connection to go out, and this guy has a connection to go out, each of these connections to not collide to each other will be assigned a new port number as well here, a different source port number. Source IP address changed to the global IP, the real IP, and the port number changed to a different number so that they don't collide to each other. So that is the general idea of NAT. We'll describe the detailed mechanism slightly later. What's nice about NAT is this: we don't need to ask the ISP for a block of IP addresses, which is very expensive. 1 is enough, save us lots of money. There are 3 more benefits, in fact, using NAT. One is this: if we want to change the IP address in the local network, we just change it. It's not like we're changing the IP addresses of the gateway there, which is a global ISP, which is assigned by the ISP. Then we need to inform the ISP we're changing it to somewhere else. Otherwise, traffic is not going to flow through. Okay, but if we're just changing the local machine, then there's no need of informing the ISP. Nice, convenient, so save us time. Third benefit: well, if the ISP is not providing good enough service, we can actually switch to different ISP. And the IP addresses we have on the local machines, we don't have to reconfigure them. Yeah, we just stay using the same fake subnet address, fake IP addresses. The last benefit is slightly unexpected to many of you. Okay? Those devices inside the local network, those 10.0.0.1, 10.0.0.2, those IP addresses are fake ones. Packets originated from outside, from the internet, carrying destination 10.0.0.1 is not going to flow through the internet and reaching the gateway and therefore coming back to the host. Because the IP address of the gateway is what? 138 something. That's the real IP address. That is also what people call the global IP address. And that fake address there is the virtual address, the subnet address. Okay? So subnet or virtual address or fake IP addresses are not addressable. By not addressable is what I meant is packets coming from originated from outside just have no way of reaching. Okay? So they are therefore not visible from the internet, not visible from hackers in the internet. So it's a security plus, okay, unexpectedly. Yeah, so we have August here who is very insightful and is sharing how much an IP address costs. If it's just for rental, $1 per month and $40 per address if we buy it out. Okay, very good to know. It might be a little bit cheaper than I have thought. All right, and next, let me try to make sure that I explain exactly network step by step using an example. So this video, 4 minutes. Net's mechanism is quite straightforward. Only 3 steps, 1, 2, and 3. Step number 1, you heard about it a bit already. So this is to handle when packet is going out from the local net to the world. We'll have to replace the fake IP address with the real one. We'll also replace the source port number with a new port number. Okay, so the source IP address, the source port number, these 2 fields are replaced with these 2 values. And this pair, so 1, 2, 3, 4, okay, are also tracked, okay, being remembered in NAT's translation table. So the source IP and the source port number, as well as the translated source IP, source port number, will be maintained as a pair in the translation table. So when the remote host receiving this packet and sends back a response, in the destination IP address, it's going to be the real IP address, and it's going to be the new port number. So that packet coming into the local net, the net box there is going to look up the table and find the pair, right? So it's matching this IP address and matching this new port number, and therefore translate the IP address back to the corresponding port IP, source IP address, and translate the port number to the corresponding original source port number. And therefore, you see the destination fields is going to be replaced by the original IP and the original port number. And that packet then will travel the local network and reaching the destination. Let's use some animation to illustrate, it will be easier to understand. So the local net here, using a fake subnet address. So this machine here, 10.0.0.1, is sending a packet to a web server, okay, outside of the local network, okay, inside the internet. The packet is going to look like this. Source IP being the fake IP. Source port number being the port the web browser is sitting on. Destination IP, the server's IP. Port number, the web server's port number. So that packet is going to reach the net box in the middle, and this is going to be replaced. This is going to be replaced. So 10.0.0.1 is going to be replaced by the real IP. And the 3345 port number is going to be replaced by a new port number generated by the net box here. Step 2, the net router there is going to add an entry into the translation table so that we know this old IP, this old port number is now being changed to this new IP and this new port number. When this packet reaches the web server sends back a response. Destination address will be the source of the request. Okay? So destination port, the source port number of the request. Now this packet will come back to the net box in the middle, and one more translation is going to be done. So this time, the process exactly is this. Let's look at the destination port number and then go to the table. Look up the entry in the table such that the port number in the WAN part matches the destination port number. Now, destination IP address is definitely going to match the WAN side of IP address because the WAN side IP address is going to be just 138.76.29.7. So this unique new port number is the key. So destination port number, you look up this value in the translation table. Identify the entry, and then replace the destination IP address with the LAN side address. Okay, port number also with the LAN side port number. And that's why we see destination IP address, now the fake IP. Port number, now the original browser's port number. That's how net works. Yeah, it's quite straightforward. And the last video, okay, it seems that NAT is very convenient, easy to use, and mitigate the IP address shortage problem. But there are some concerns, okay. This video, about 5.5 minutes, talks about the concerns. Last are the drawbacks of NAT. Point number 1, port number, pretty short, 16 bits only. That is also saying we could have only up to 60,000 simultaneous connections. If the local network there is for home use, this is plenty. But if the local network there is for enterprise use, if a company is there trying to save money and subscribing to only one real IP address, having lots of employees, lots of machines inside, chances high the packets going for one flow might be mistaken, okay, with the other flows. Point number 2, NAT is controversial. In the previous slides, you might see the authors of the textbook referring to these NAT devices as NAT routers. But routers are what? These devices in the core of the internet. Now, routers implement only 3 layers of protocol: physical, link layer, and network layer. So routers are also called the layer 3 protocols. Now, layer 3 protocol is supposedly only accessing layer 3 packet header. Layer 2 protocol accessing layer 2 packet header. NAT, if you think about the mechanism again, it's what? Replacing the IP address fields in the packet header. It's also replacing port number, okay, the port number fields in the packet header. IP address, that is a field in the, layer 3 packet header. We learned about the IP packet format already. But port number, if you recall, in chapter 3, the transport layer, port numbers are there to differentiate different processes running on the host. It's actually a layer 4 notion. It's in the transport layer header, in the layer 4 header. So NAT as a router should not be doing that. So those who are against NAT boxes to address the network shortage, IP address shortage problem, okay, argue that we should probably, improve IPv4 such that we have more bits for the IP address field. So IPv6 is the next generation. It's using 128 bits for the IP address, much longer. We'll talk about this later. Point number 3, NetBox. Hosts sitting behind NetBox cannot be reached from a machine from outside. So that was actually presented as a benefit, a security benefit earlier, right? Hackers cannot be sending packets to 10.0.0.1 because that packet is just not going to go anywhere. Okay, not even reaching the NetBox in the middle, the IP address being 138. something something. Right? Only packets with the destination address 138. something will be able to reach NetBox. Okay? And NetBox there, it will also not know, right, what port number, what local IP address to convert back to reach 10.0.0.1. So it's actually hard to reach local hosts from outside. So if packets are originated from outside, that's not going to work. Packets originated from inside, however, works. Now we know, right? So from 10.0.0.1, the box tracks the local IP address. Okay, keep it in a table. That packet gets translated using global IP, using real IP, goes out. Packet will come back to the router and the NetBox. Look up the table and then translate back. So originated from inside, no problem. But data originated from outside, big problem. And this is a serious problem for these designers, P2P protocol designers. In P2P protocol, a lot of time we will try to establish connections between one user's host to another user's host. You and me being hosts, we are, chances high, sitting behind the net box, sitting behind the net router. So we will have trouble calling directly to each other, setting connection directly to each other. If you recall in Skype's protocol design, making a call, the designer of Skype actually take extra step. Okay? Bob and Alice will need to call a relay peer, and the relay peer will exchange packets for each other, okay, for these two peers, for Alice and Bob. So application layer designer now need to worry, okay, in case layer 3 or layer 4 protocol is going to break. Okay, unexpected might happen. So one layer's protocol designer needs to worry about another layer's, how it's designed, how it works. That's breaking the end-to-end argument. So by this here, okay, what I'm saying is this. The reference protocol stack there, okay, application, transport, network layer. So we say nice about building the network protocols and separate them by layers so that it's modular. Designer in one layer does not need to care about what's inside another layer. Exactly the same thing we are arguing here. Application layer protocol needs to worry about another layer's protocol, how it works. So that breaks the modularity there we have in the original reference stack. And that is what end-to-end argument is referring to. All right, so that's NAT. People have concern. First of all, there might not be enough pore number space to accommodate all the connections from inside and out. Second, if you change port number and address at the same time, you are editing the transport layer header and the network layer header at the same time, right? Then is NAT a layer 4 device or a layer 3 device or in the middle or something like that? It's a little bit hard to make everything modular as internet was designed, okay, in this stack model. Last one is tricky. Last one I think is the most critical issue using NAT for P2P applications, where you want to have connections directly to another end user. That is often not possible. Yeah, so by the way, there's a comment from Oh Yang saying that if you stay in NTU Storm, you get a free public IP address. Good for you. Okay, it's useful if you want to set up some sort of server. Because with the public IP address, then other end users can connect to you directly. So therefore, you can host a server. And you can also be a contact point for the P2P applications, for sure. Remember everything when you graduate. It's going to be a mess. Okay. Yeah. And you know what, guys? It's time for quiz 36. Let me see. Yeah, we go to quiz 36. And the topic is called ideal versus practical. So Q1 asks, would you prefer paying for multiple IP addresses or using NAT? Okay, so this is about in case you have multiple devices like Polly has here. Okay, all need to be connected to the internet. Would you rather pay for multiple IP addresses or using a NAT box, which is one-time cost? Well, each IP address appears to be a one-time cost, but it isn't. It is not exactly cheap. Okay, so that's Q1. Tell me whether you prefer buying multiple IP addresses or just using NAT, and why. Q2. Would you prefer using NAT or IPv6? Okay, so NAT, IPv6 is this next version of IPv6 where we use 128-bit for the IP address space. So we could have 2 to the power of 128 IP addresses. Okay. So would you prefer using NAT or using IPv6, and why? All right, let's go to okay, I think team 3 here has already typed up their solution. But you know what? for this quiz, you can see that it's a little bit open-ended, right? I mean, the reason you have to support one solution versus another could be a little bit subjective. So Polly is not looking for fast solver, okay, to give bonus this time. So instead, I'm looking for unique, okay, reasons to support your choice. So hey, it's time to gather your teammates if they are here. Have a short discussion. You have 4 minutes to discuss and 1 minute to type up your solution. Ah. All right, that's about time. Yeah, so let's go through some of you guys's. Let's go through some of you guys's opinions here. So Team 3 says they prefer NAT because it's cheaper. Yeah, if money is the main concern, we go with NAT. But if you are starting a company and you expect that the demand to grow, then of course you try to purchase or rent IP addresses. That would ensure that you can accommodate all the connection needs and not being controversial and allows P2P communication, right? Allow hosting servers, okay, and on top of all that. Q2, I mean, I see very often that you guys say, hey, NAT first, okay? But later on, if I'm rich, then I go buy more IP addresses. That seems to be the common idea. And then choosing IPv6 for its for its expansion of IP addresses. I think that's what you meant, Sophia. Expansion of IP address space. Yeah, because IPv6 appears to be the solution that tackles everything once and for all. Because with real IP address, again, right, you can accommodate P2P application. You can host services. Yeah. So exactly, if you choose non-NAS solutions, that means if we could avoid all these concerns people will have using NAT, then we can try to avoid them. Yeah. There was a very interesting answer from Team 2 about Q2. So Team 2 said, I would rather use NAT instead of IPv6 because my registrar doesn't support IPv6 at the moment. Yeah. Yeah, because IPv6 is not yet everywhere. And that is something that we're going to talk about next. Okay. And I see that there's a conversation going on the chat. Which registrar did you use? I use Gandhi, 4.tw, IS, and FI, and AX. Oh, wow. Okay, there are quite a few registrars, okay, that you are utilizing there. Okay. Yeah, I think there are more and more IPv6 compatible registrars. I don't know whether they charge more. So that's something that I don't. I suppose they charge more. Okay, good. We get the idea. Team 1, 8, 6, and 12. Well, Polly will definitely come back to look at your solutions. And 12. So, yeah. Oh Yang, you are actively discussing at the chat and in the meantime contributing in the Discord channel. Okay, but I think you get the idea. NAT does not. I mean, it mitigates the problem, but it's not the ultimate solution, right? Now that's dig into the ultimate solution. So let's expand the IP address space to 128 bits. So this very brief, short overview video is telling exactly what I said. Okay. Last topic in 4.3, the IPv6. This is also the protocol some of these network engineers thought more legit, addressing the IP address shortage problem, instead of using these controversial net boxes. And that is why we actually upgrade from version 4 to version 6. The approach is very straightforward, expanding the 32-bit IP address space to 128 bits long. So the main goal of having IPv6 is exactly this. There are two secondary goals. First is to speed up the processing or forwarding of the packets as they come into a router. So in the data plane, packets coming in really, really fast. If we could reduce the forwarding time, processing time, we make the transmission process as efficient as possible. Okay. So you see in IPv6, the header is also changed, okay, to try to reduce the forwarding time, the processing time. The secondary purpose, this. We want to add something so that we could label the packets, so we could separate a group of packets from other, okay, and make them flows, different flows. Now, with the different flows of these packets, we could then assign priority to a specific flow versus lower priority for other flows. Okay. Therefore, okay, we could establish a more flexible levels of quality of service for these different flows. You see also header fields there to support labeling of flows, setting priority of the flows. Yeah, so you see, the motivation of IPv6 is not just as simple as we want to expand the IP address space, but also a few other things. The next video is going to be long, 7.5 minutes. In the first part, you will see Polly analyzing the IPv6 header size. So you will see that the IPv6 header is designed such that it's as compact as possible, but the header size is still larger than IPv4. In the second part, you will then see the IPv6, the packet header. What are the fields there? The IPv6 packet format. The header part of it is fixed size and 40 bytes long. Now recall version 4. Is it fixed size or variable size? It's actually variable size because of the option fields there. So that field, in case we have more options, then it's going to go longer. No fields, 0. And therefore, IPv4 header size is 20 bytes minimum and could potentially be more. Okay. Now you probably recall, right? When we were talking about the IP header size, 20 bytes, we also mentioned the TCP header, 20 more bytes. Together, 40 bytes, just to store the control information. If we're sending a real message that's 10 bytes long, the entire packet will be this long, while only 10 of them is effectively sending data. This is very low utilization. So yeah, Polly kind of promised you that in the next version of IP, we're going to reduce the size of the header. But you see here, is 40 longer or 20? Yeah. 46 in fact has a longer header. But this is necessary, and this is as small, as short as possible already. Allow me to explain. In the IP packet header, there are two fields called the source IP and the destination IP. In version 4, the IP address space is only 4 bytes long. Now, to store source and destination IP, you only need 8 bytes. But in version 6, the main goal is to expand the IP address space. So unavoidably, we have very long IP address, and two of them, one for source IPs, another one for the destination IP, together 32 bytes. If you look at this, version 6 header 40 bytes, so we have only 8 bytes for the additional fields. While in version 4, 20 bytes long, we have 12 bytes for the additional fields. So the designer of IPv6, you see, try very hard to reduce these other unnecessary part of the header, removing these fields away from the header. Okay. So 40 here, longer indeed, but it is actually after we try very hard making the header part as compact as possible, as small as possible. In fact, the second feature of the version 4 header is this. To recall, in the fragmentation and reassembly function of IPv6, we have these 3 fields in a row. ID, fragmentation flag, and offset. This row of extra header fields remove entirely, okay? And this is done by disabling the fragmentation and reassembly function in version 4. So in IPv6, no longer allowing fragmentation. And this is why we see version 4 header, although longer, it looks really clean and compact. Okay. First, the source address. Second, destination address. And the rest is only just 6 more. 1, 2, 3, 4, 5, 6. First, here is the payload length. If you recall in version 4, we do have what? The header length and the entire packet length. Because the header size can vary. And the packet size, because the data size can also be different, so we need 2 lengths. Here now, having a fixed packet header size, we need just the payload part, okay, the payload length to indicate the size of the data down here. Hop limit, this is just the TTL field, okay, just like in IPv4. Next header, it looks odd, we've never seen this before, but this is really the upper layer field in version 4. So what it does is, once we extract the payload, we actually forward the payload to what's indicated by this pointer here. And so further processing will be done using this handler on the payload. The version field. We also have this in version 4. So the only difference is that this value will always be 6 in version 6. Priority and flow label. These two are new. So flow label here is to allowing us to group a specific set of packets together. So coming from one application, coming from one service, they could be carrying flow ID 1, and other packets from other services, flow ID 2. So we could identify packets for one flow, and packets for yet another flow. So we could separate these packets traveling the internet. As a result, we could then provide different priorities to different flows. So some flows will go earlier than the others. Therefore, we provide flexible levels of these QoS. Now, there are some more fields we remove, not just the fragmentation fields. The header checksum in IPv4 header, that is removed because to calculate checksum takes time. To check the checksum takes also time. So let's try to reduce the forwarding processing time as much as we can. So let's remove the checksum part. And take the risk of some bits in the header being flipped. We might have some, we might run into some errors, but chance is very low. We way higher here, way more here, trying to make sure the forwarding part is fast. And we move the option part down to the payload so that when we grab the payload and give it to the handler is going to look at the first few lines in the payload, and those will contain the options. There's one more thing. ICMP version 6. What is ICMP? You need to think back. In one of the earlier overview slides, I was talking about the functions and protocols implemented in the network layer. In the data plane, we have forwarding. In the control plane, we have routing and management. ICMP is one of these protocols implementing the management function. So we also extend the version 4 ICMP to version 6. And the reason we need the version 6 ICMP is so that we could send a special message, packet too big. Allow me to elaborate. Now we don't have fragmentation and reassembly, but the fact that some of the links on the internet allows smaller MTU is still there. So what if we have big datagram coming to a router and the next link is saying MTU smaller? But we cannot fragment this datagram anymore. What should the router do? What can the router do? So the mechanism in version 6 is to send a special message, an ICMP version 6 message, back to the data source saying packet too big and the better packet size is below this MTU value. So there's additional message being defined in ICMP version 6, allowing the routers to manage themselves, deciding what is the best datagram size. And we'll just ignore this part. Multicast, we'll just not talk about it at all. It's a can of worms. So this is IPv6 packet format. All right, so next video is exactly what Miguel was asking for. You see that, hey, we were originally all in IPv4, right? And then we need to move to IPv6. So all these routers originally running IPv4 will need to be upgraded to IPv6. But you see, there's so many routers on the internet, right? You cannot be doing like, a flag day that we change the version all at once. So it's done more in this gradual fashion. So some routers will be capable of IPv6, IPv4 and 6. Some routers are still limited to do IPv4. But then how would such a IPv4 cloud or subnet interact with a IPv6 subnet? There's a technique called tunneling. And I'm sorry that we will need to use maybe a few more seconds time this week. So that video, 6 minutes. So this topic is a little bit special, We will be talking about how we move from a IPv4 internet to a IPv6 internet. You see, There's no way we turn down all the routers in the world and upgrade to version 6 simultaneously and turn them back on and hope that they will just work. No way. It's really, really risky. And hey, we are all living in different time zones. What do you mean by having a flat day? And not to mention that turning the entire net down for an entire day, okay, and wait until all the debugging and upgrading is done. Well, yeah, some part of the world might panic. So how will the network operate with part of the internet running IPv4 and some other parts running IPv6? So transition from IPv4 to IPv6, this is what we meant to talk about. How do we allow the mix of IPv4 router to IPv6 routers? And the technique, okay, let me tell you ahead of time, is called tunneling. Okay, establishing tunnels, okay, between routers, okay, at the edge of the IPv6 network to IPv4 and then back to IPv6. And the technique is working this way. So if there's a packet generated from the IPv6 space, so then the network layer in the machine in the IPv6 space will be generating an IPv6 packet. Okay. Once it hits this border between IPv6 and IPv4, this router standing at the border will be implementing both IPv4 and 6. Okay. So this router will also be doing this. Okay. Take the IPv4 packet generated from the take the IPv6 packet generated in the IPv6 space and encapsulate that into an IPv4 packet. Okay, so this is the IPv4 packet, okay, and this is the original IPv6 packet, okay, generated from the IPv6 space. So that IPv4 packet is encapsulated, so being contained, okay, in this bigger IPv4 packet. All right. So you see here, we'll have packet header fields here, source IP address, destination IP address, and etc. etc. Now, IPv4 packet here coming from the border of IPv4 and IPv6 connection is going to travel the IPv4 network fine because the header fields interpretable by the routers in the IPv4 space, and eventually reaching the other end, okay, the other border between IPv6 and IPv4, and that border router there would extract, okay, the IPv6 packet, the blue part here, from the IPv4 packet, and then forward it further on onto the native IPv6 space here. Right? This enables an IPv6 machine talking to an IPv6 machine with the middle part being IPv4. I know, allow me to illustrate. So in the scenario, we have an IPv6 space to the left and another IPv6 space to the right. I suppose we have data we want to send from A to F. Okay? Both of them, version 6, they should be able to send data to each other all right. Now the problem is this. Yeah, an IPv6 packet here will travel through the version 6 space. But as soon as it hits the version 4 space, yeah, these routers, they're old. They don't recognize the version 4 format. They will not be able to handle the packet and forward it down this way. Okay? And that is why we need tunnel. Okay? So what's being done, okay, in the tunnel is this. B being the border router, E being the border router separating the version 4 and version 6 space. It's implementing version 6 for sure, but also version 4 as well. Therefore, B and E both carry IPv6 address as well as IPv4 address. By setting up tunnel, B now actually record E's version 4 IP address. E here records B's version 4 IP address. So essentially the two ends, okay, exchange the IPv4 address. So once that's done, usually this is done offline by the network admins. Once that is done, then let's consider, okay, A here generated the packet, the blue one, and we're forwarding it towards the destination. Right? Once it hits the border router here before the IPv4 space, B, the border router, is going to do this. Encapsulate the blue packet inside a version 4 packet. In the version 4 packet, the source address is going to be B itself. destination address is going to be the other end of the tunnel. Okay, the other end of the tunnel's IPv4 address. Now, this is an IPv4 packet, source being B, destination being E. Then the IPv4 network is capable of forwarding this packet over, okay, at least to E. So E is going to receive the packet next, and being the border router, and being the other end of the tunnel, E is just going to extract the blue packet out of the red one and forward it down to the rest of the IPv6 space. And this is when F here receive the packet that is supposed to go for F. All right, so that's how you interoperate IPv6 space with the IPv4 space in the middle. Okay, so tunneling is the technique. Good that it's doable, interoperating two different spaces. Now, that's all the time we have today. I have actually one short video, but it's okay. Let's play that and talk about the IPv6 adoption rate next Wednesday. All right, so with that said, and by the way, quiz 37 is also about IPv6 adoption rate. With that said, I would say that's all for today, and I see you tomorrow morning for the exams. Okay, bye. Okay, bye. Yeah, so you're right. We have only one quiz due this Saturday. The Google Meet session is open for questions Thursday noon. Okay, so if you have questions about the exams, I would suggest that you write to ask. Okay, Isa, I hope that answered your question.